Welcome to the second day of summer general physics. In this fifth video, we'll be taking a look at acceleration. Just as we saw velocity was a change in displacement with time, acceleration is defined as being a change in velocity that occurs in some time period. So this can happen three basic ways. You could have an object speeding up, it could slow down, or it could change in its direction. And of course, it can be doing multiple of these things at the same time. Acceleration is a vector, just like velocity is, and we define the average acceleration as being the change in acceleration, delta v, which is defined as being the final velocity minus the initial velocity, divided by the change in time, or the final time minus some initial time. If we look at this equation for acceleration, we can see what the units of acceleration must be. We know that velocity is meters per second, or a distance that's traveled in some amount of time, and then time, of course, is seconds. So dimensional analysis tells us that the units of acceleration would be meters per second squared. If we make a graph of velocity versus time, then the acceleration will be the change in the velocity over time, or the slope of a straight line that connects the final and initial points of our motion. So if we think about the relationship between acceleration and time, we can see that the direction of the velocity vector and the direction of the acceleration vector are related to each other and depend on the motion of the object. So if you have an object that's speeding up, the velocity and the acceleration vectors point in the same direction, and the velocity and acceleration would have the same sign if the motion is in one direction. If, on the other hand, the object is slowing down, the velocity and the acceleration would be in the opposite direction and have opposite sign. So in this series of pictures, you can see a multi-flash image of a car that's moving. A multi-flash image is one where you pretend that an equal amount of time has passed between each one of these images. So with series A, you can see that the car is an equal distance in each subsequent image, implying that its velocity is constant. So it's traveling with zero acceleration. In the second image, you can see that the car is speeding up as there's greater and greater gaps between the images of the car as time goes on. So this means that if the velocity of the car is forward and it's increasing, and the acceleration is pointing in the same direction as the velocity, you can think of it as the acceleration vector adding additional velocity to our velocity vectors. On the other hand, if the car is slowing down, the velocity and the acceleration are in opposite directions. So you can think of the acceleration vector as nibbling away at the velocity vector and making it shorter, making the velocity smaller. So here's a question for you. If a car is traveling east, will its acceleration be eastward? So give that some thought, pause the video, and choose your answer. Okay, so now that you've had some time to think about it, we'll have to ask ourselves, this car is traveling east. Is its acceleration eastward? Does that necessarily have to be true? Well, if it's traveling east, its velocity must be eastward. The velocity points in the direction of travel. But what if the car were slowing down? If the car were traveling eastward, but slowing down, its acceleration would be opposing its velocity, nibbling away at it, and so its acceleration would actually be in the westward direction. So this question, or the answer to this question, would be false. If a car is traveling east, its acceleration must not necessarily be eastward, although its velocity would be eastward. How about this question? An object with constant non-zero acceleration can never stop and stay stopped. Is this true or false? So pause the video and give this question a little bit of thought. Okay, so now that you've had some time to think about this question, let's take another look. An object with constant non-zero acceleration can never stop and stay stopped. So if an object has a constant non-zero acceleration, that must mean that its velocity is always changing. Its velocity is always changing. If something is stopped and it remains stopped, then the velocity is zero, and it has to stay zero. But if there's an acceleration, a velocity can never stay zero, it has to change. An object's velocity could be zero for an instant. So you could have a car that was moving forward, and then suddenly the driver, say, threw the car into reverse. The car would slow, stop for an instant, and then start speeding up backwards. But it could never stop and stay stopped if there is an acceleration. So displacement, velocity, and acceleration are all related to each other. We've seen that velocity is a change in displacement with time, and acceleration is a change in velocity with time. The fact that they're related in this way means that their graphs are related too. So in this first graph of displacement, you can see the displacement of an object with time, and you can see that the displacement is increasing, so the object is moving forward. And if we take a look at the slope tells us how the displacement is changing, what the rate of change is. So the slope of our displacement curve is actually the velocity. So if you want to know the velocity of an object and you have a graph of its displacement, you can look at its slope at any point and construct the velocity. In this case, we see that the slope is getting steeper and steeper, and so that means our velocity is increasing. Likewise, the slope of a velocity versus time graph gives us the acceleration. In this case, we can see that the slope is constant, and this implies that our acceleration is a constant value as well. So here we can see that there is this relationship. Since velocity is a change in position with time, the slope of a position graph gives us the velocity, and the slope of a velocity graph gives us the acceleration. We can work our way backwards too, actually, by looking at the area under the curve or line. So if we started out on the other side with our acceleration graph, and we considered some amount of time, let's say right here, you can see that if we look at the area under our acceleration graph at this instant of time, it would be this much. If, on the other hand, we considered a little bit time later, so let's call that time 1, and maybe this is time 2. At time 2, there's more area under the graph. And likewise, as we go along, if we go from the y-axis out to our chosen stopping time, there's more and more and more area. The area under this line gives us the velocity. And we can see that indeed, as we go from increasing time 1 to time 2, which would maybe be here and here, the value of the velocity is increasing, just like the area under this line is increasing. Also, we can do the same thing by going from velocity to displacement. If we chose a time and we look at the area under that line, under the velocity line, that area will give us the value of the displacement at that point. And here we can see if we choose some later time, then there's more area, and that corresponds to the value of the displacement at that later time. So by looking at slopes, we can go one way. By looking at the area under the curve, we can go the other way. Actually, there may be some starting velocity or some starting displacement that we need to worry about. But we can certainly get the rate at which it is increasing. So here is another question for you. Above is a multi-flash image of a puck's motion. So this series of images at the top of the slide. Which line on the graph below would show best the puck's acceleration? So in this graph, which one best represents the puck's acceleration? Is it the red line, the green line, or the blue line? So pause the video and give this some thought, and then come back when you have your answer. Okay, so now that you've thought about this problem a little bit, let's take a look at these options. And let's take a look also at what the puck is doing. So first off, let's consider this middle region. So in this middle region, there's about the same amount of distance between each one of these pictures. So since there's the same amount of distance, and we're assuming that these pictures are taken at equal time intervals, then that must mean that in this central region, the puck is traveling at a constant velocity. If it's traveling at a constant velocity, not speeding up or slowing down, then the acceleration is 0. So the graph we should look at would be close to 0 in the middle. Over here on the left, the puck is speeding up. The distance between the images is getting bigger and bigger, so since it's speeding up, the acceleration would be positive. On this end, the puck is slowing down, and so if it's slowing down, the acceleration would be negative. So I would actually pick the green line, because I want something where the acceleration is 0 in the middle, because the puck is moving at a constant velocity, is positive while the puck is speeding up, and negative indicating that the puck is slowing down at the end. So there is a special case when acceleration is constant. If you have constant acceleration, and if your motion is in one direction, then there are several constant acceleration motion equations that you can use. And you can see them listed here on the left-hand side of the slide. This looks like a lot of equations, but it actually makes life way simpler for us to have all of these different options. Because you may encounter a problem where you know something about velocities and acceleration and need to find something out about time, and then maybe this would be the most efficient equation to use. Or you might know something about displacement and acceleration and need to find out something about velocity. So whenever you encounter a problem where you have constant acceleration, you should follow these problem-solving steps. First, it's really helpful to draw a picture of the problem so you can get a handle on what objects are involved and how they're moving. Then you write down the knowns. What are the numbers that are given to you in the problem, and what do those numbers correspond to? Are they times? Are they velocities? Are they accelerations? Then write down the unknown for your problem. What are you trying to solve for? What is the problem asking for you to find? Then you look for an equation that has just the things that you know, and maybe the one thing that you don't know, and solve for that thing that you want to find algebraically. Now this is an important step and one that often is neglected, because the temptation is, once you have an equation, to plug in the numbers right away. But that can actually make life harder, because if you do just one mistake with your calculator, you may have to go back and do the whole problem again. Whereas if you solve for the unknown algebraically first, then you have just an equation that you can plug numbers into, and if you make a mistake with your calculator, it's much simpler. You have to do a lot less work to find a numerical answer. So finally, once you have your equation in the form that you need it, you can plug in your knowns and calculate. And keep in mind, there's usually more than one way to solve problems. Often, one student will pick one of these equations, and maybe someone else picks a different one, and they should both get the same answer. So next, we're going to be looking at some examples of problems we can solve with these equations of constant acceleration. Before you watch the next video, make sure to watch the video that's labeled Apollo 13. You'll want to watch that since our first example will pertain to that video.